This is T1 steel, the most important development in alloy steels in the past 40 years. It is more than just another steel. It has such a unique combination of properties that it may well be called a new engineering material. It has proved itself in many ways, and one of the most effective demonstrations took place in Birmingham, Alabama. The project was Operation T1. The time was June 1954. On this day, some of the nation's top-ranking authorities on steel applications saw dramatic proof that T1 was a new advance in alloy steels. The project was built around a series of pressure vessels, each made of half-inch T1 plates. Half of the vessels were stress-relieved after welding, and half were not. Each of the vessels was to be subjected to the same destructive tests, and the results were almost identical. A burst test was the first part of Operation T1. The vessel was cooled down to minus 45 degrees Fahrenheit. If T1 had any tendency to brittleness, it would certainly become evident at this extremely low temperature. With a panel set to measure every phase of temperature and pressure, the signal was given to activate the pressure pump. The test was on. When pressure reached 1875 psi, T1 already showed 3 times the yield strength of ordinary steel. But how extraordinary was it? It held at 2,000 pounds. It passed 2,500. Finally, at 2,850 psi, the vessel burst at a pressure 7.5 times the maximum now required for equipment of this kind. After such a burst, even at this frigid temperature, T1 showed no evidence of brittleness or shattering. Note the simple tear. Incredible ductility for an alloy steel having such a high strength level. Other vessels subjected to similar burst tests ruptured at about the same pressure, demonstrating the same remarkable degree of toughness. All this with a half-inch plate of T1. Had carbon steel been used, the plates would have had to be 3 times as thick to withstand that much pressure. The impact test was even more brutal and dynamic. The vessel's temperature was dropped to minus 38 degrees Fahrenheit, and its internal pressure raised to 1,875 psi, the nominal limit for T1. Here certainly were adverse conditions for meeting the colossal hammer blows in store. Suspended in the 150-foot tower was a massive weight, ready to hurtle down with devastating impact. This tub, weighing over 13 tons, was raised to a height of 52 feet for the first drop. A force of almost 1.5 million foot-pounds. Yet below the saddle there was no more than a slight dent. For its second drop, the top rose to 73 feet. A shattering impact of almost 2 million foot-pounds, and there wasn't even a leak. The distortion increased, but T1 still held. For the third drop, the top was raised to over 100 feet above the vessel. T1 had already proved its superiority. This was to be the crusher. It took almost 3 million foot-pounds to rupture the vessel. There was no question that T1 had remarkable mechanical properties. And again, the experts were surprised by the kind of rupture, an absolutely clean tear, despite the terrific impact. Here was conclusive evidence of T1's unique properties, a combination of ductility and toughness not usually expected in the same steel. A second series of tests confirmed the dramatic performance of T1 steel. The results were almost identical. Again and again, the unique combination of toughness and strength was conclusively demonstrated. When Operation T1 ended, the engineering and technical authorities present were truly amazed at what they'd seen, while to U.S. Steel, this was just another step in the research and development of T1. Prior to this demonstration, we spent years testing this material in many other applications. Behind its unique qualities are many things. First, a judicious combination of elements chosen with specific properties and the price book in mind. Carbon, held to approximately 0.15% for improved weldability. For hardenability and toughness, we found that manganese and nickel could be held to 1% maximum, and chromium to about 0.5%. Molybdenum of around 0.45% was used for depth of hardening and high temperature strength. Copper of about 0.30% was used to improve atmospheric corrosion resistance. Small amounts of vanadium made possible high tempering temperatures and improved welding. We found a little boron to be the least expensive way to further increase hardenability. And here is a typical heat analysis, with all elements falling within a fixed range to create a highly versatile steel. But to produce a steel which can take the punishment of Operation T1, two basic steps are necessary. It must be quenched and tempered. The as-rolled plate is charged into a furnace and heated to 1650 degrees Fahrenheit. It has not yet been trimmed to size, since from the side and end crop we will later obtain enough test material to be sure the high quality standards of T1 are met. After thorough heating at this temperature, the plate is water quenched to room temperature. To do this, low carbon is a must, for only with low carbon can we quench from so high a temperature with no danger of cracking. The tempering which follows is done at 1200 degrees. When necessary, the plate is flattened in the roller leveler. Both water quenching and tempering are carried out under precise time and heat controls, for it is these two phases which give T1 the structure aimed for. Low carbon, tempered martensite, the toughest microstructure in steel. Note that there is a distinct difference in the microstructure of T1 as compared with A7 carbon steel. The effects of the difference are quite impressive, especially in mechanical properties. Yield strength of A7, 33,000 psi. T1's yield strength is almost triple that, 90,000. Tensile strength of A7, 60,000 psi. T1 with 105,000 psi registers 75% higher. Next, a wonderful reversal of form. It is expected that a carbon steel like A7 will have excellent elongation, and it does, 22% for a 2-inch length. But the very properties needed to create a tensile strength over 105,000 psi are expected to cut down elongation. Yet, T1 is completely different. In a 2-inch length, its elongation is 18%, very close to conventional steels. Yes, here is a unique steel, ready for an exceptionally wide range of uses. In plate gauges ranging from 1/4 inch to 6 inches, and it comes in a full range of bar sizes. But, asks a practical engineer, what about fabrication? For example, how sensitive is T1 to cold forming? The effect of cold forming on the toughness of T1 has been carefully measured, and actual applications have confirmed the fact that T1 is less sensitive to such treatment than most steels. Doesn't flame cutting affect the edge toughness of T1? Naturally, the flame cut edge will be considerably harder than the rest of the plate, but still so tough it will show no cracks at all. What are the limits on T1's machinability? Since its introduction, T1 has been put through all the normal machining operations by its many users. Large tonnages of alloy steels have been machined at the strength level of T1 with no particular difficulties. The machining practices used on T1 should be similar to those employed on any steel of similar hardness. Now, what about welding? Where stress relieving is necessary, a 90-15 electrode will provide at least 90% joint efficiency. But usually no stress relieving is required, in which case a 120-15 electrode will give 100% joint efficiency. Of course, Operation T1 highlighted its excellent low-cost weldability. You recall that half the pressure vessels were stress relieved and half were not, yet the difference in joint strength was negligible. This and all the other remarkable qualities of T1 are more widely recognized with every passing day, and the demand for T1 is rising very rapidly. Tons of it are being shipped weekly to meet the ultimate test of any material, its practical application, and its cost compared to other usable materials. Here again, the actual record of T1 is quite eloquent. This skip car hauls coke, limestone, and ore. Steels formerly used as bottom, side plates, and bale cover lasted about 2 months. Changing to T1 increased the service to well over 7 months. Before T1, 9% of all delays on a slabbing mill were caused by failure of the chain on this scrap butt conveyor. Butt ends used to twist and break the links. Since the installation of T1 links, the mill has had practically no downtime due to link failure. The steel lips in this bucket, operating in temperatures up to 600 degrees Fahrenheit, used to last 1 month. The new T1 steel lips lasted over 11 months. The pockets of this transfer car were subject to such abrasive wear that yearly replacement was required. But with T1 steel, 2 years passed and replacement still seemed far off. Here is an outstanding example of resistance to wear at high temperatures. Flue dust carried at high velocity in an air blast eroded this pipe at the elbows. Special abrasion-resisting steel patches used to last 3 to 4 weeks. T1 patches were substituted, and after 21 months, were still in excellent condition. This brawny mover of mountains is a Colby wheel, made tougher with the use of T1 at every spot where the going's really rough. The lips and teeth on these buckets, all T1, gouge out tons of overburden at every turn of the wheel. It's obvious that in such an integrated operation, any downtime is very expensive. But with T1, breakdowns are sharply reduced and overall efficiency boosted. The steel in a turbine disc must withstand high stresses at high temperatures and at speeds up to 3,600 RPM. It formerly called for very high-cost alloy steel forgings. Now, rolled T1 plate is used. The switch required no change in design, posed no fabrication problems, yet T1 cut material cost by 60%. In modern wind tunnels, tremendous forces are generated by air propelled to many times the speed of sound. At certain critical areas, it takes a really tough steel to withstand these high winds. It has been found that T1 steel is ideal for such critical areas. These flex plates must have a high degree of toughness, strength, and ductility. T1 has proved itself so superior to steels previously used that at last report, 3 modern wind tunnels all called for T1 flex plates. Matter of fact, the authorities concerned are now using T1 in other related areas. For example, these air storage tanks to be used for wind tunnel operation are drastically reduced in weight because they are made of T1 steel. These Freon gas storage tanks are also built from T1 steel. Just another example of T1's excellent application wherever exceptional qualities are needed to resist internal pressures. The use of T1 steel in mining operations is increasing by the day. These cars, like most mining equipment, are subject to a great deal of impact abuse and abrasion. And because of this severe punishment, maintenance and replacement costs are very high. The ore cars involved in this particular operation were not made of T1, but for all the replacements ordered, T1 was specified. The initial replacement cost may be slightly higher, but the ultimate savings are substantial. Many parts of these mine cars have been changed to T1 steel because of its long-run economy. These are some of the many mine cars which have proved T1's value in the field. Varied applications? Yes, indeed. Forest clearance is another field where metal is subject to all kinds of stresses, severe abrasion, and impact abuse. The blades used on this cutter are, of course, made from T1. Since the change to T1, there has been a drastic reduction in maintenance costs. This application, like the others shown so far, involved no actual change in the size of any section. But where change in size or weight is possible, the savings are even more dramatic. For example, before T1, the capacity of this mammoth shovel was 35 cubic yards, and many of its parts were made from expensive, heavy castings. With T1, the bucket, lips, bale, and dipper stick are fabricated. The life of each part is expanded. But here's the big point. The weight reductions made possible by T1 increased the bucket capacity from 35 to 45 cubic yards, added 10 additional cubic yards of payload to each single bite. At last report, the shovel, working 24 hours a day, 7 days a week, had moved 30 million tons of overburden with extremely low maintenance cost. Also using T1, this shovel has been operating at temperatures as low as 50 degrees below zero in the Minnesota Iron Range. Yet, despite severe stress, impact, and abrasive shock, T1 shows no signs of brittleness, not a single failure in 3 years. In contrast to this low-temperature operation, consider these ladle hooks. With T1 available, the hooks were redesigned. They were decreased in size. Visibility was improved. And because dead weight was cut down, it was possible to increase the ladle's capacity. This trailer was rebuilt with T1, and 2 very important changes took place. Its dead weight was reduced by 6,000 pounds. Even if this were the only improvement, imagine the reduction in operation and maintenance cost in a single month. To this benefit, add another. The trailer's payload was increased by 8,000 pounds. True, the initial cost of T1 was higher than the steel previously used, but it so improved the trailer's efficiency that haulage cost was drastically reduced. The same kind of economies were made possible by T1 in this lowboy semi-trailer. The structural members of the trailer bed were built from T1, and because of its superior strength, the structure was much lighter. Result? Less dead load, more payload. And the same possibilities exist in almost every field of transportation. This LPG trailer is built from T1 steel. Its payload has been increased by over 10%, and it's still within the legal highway limits. Several major companies are now using T1 to build similar LPG tank trailers, and more are bound to follow. Whether we speak of transportation or construction, the same basic problems exist. For example, this 3-lane bridge spanning California Straits of Carquinez is a vital link in one of the nation's major highways. No longer adequate to handle the increased volume of traffic, the existing bridge is to be supplemented by a new 4-lane structure very similar in design. Engineering specifications call for 2,900 tons of T1 steel to be used in those sections that are subject to the greatest tension and the greatest compression. The T1 sections, shown in red, are a part of the top chords, bottom chords, verticals, diagonals, and gusset plates. Wherever the unique properties of T1 can be used to the best advantage, this new engineering material will play an important role. It will impart to the new bridge greater strength at a reduced weight, a major step in solving the construction problem of strength-weight ratio, just as the new bridge will be a giant stride in solving the traffic problem of this area. T1's weldability. Here's another plus in any kind of field construction. Because T1 practically eliminates the need for stress relieving, field welding is perfectly feasible regardless of location or weather conditions. For example, had T1 been used in this vessel and in constructing these power plant penstocks, welding costs alone would have been reduced tremendously. The cost of stress relieving would have been completely eliminated, and a proportionate decrease in weight would have cut shipping and construction costs way, way down. Let's be more detailed with a hypothetical case, basing it on T1's new design possibilities. Suppose we're to store 25,000 barrels of volatile liquid, which must be contained at 210 psi. And conditions call for spherical storage space to be field erected. Using conventional carbon steel, a 1,000-barrel sphere is the best we can do. A larger sphere would go beyond the limits of conventional steel. Therefore, we must erect 25 vessels to provide the 25,000-barrel storage called for. This, when compared to the potentials of T1, is a tremendous waste. For the enormous strength of T1 steel is adequate to withstand the stresses of a single field-erected sphere with a capacity of 25,000 barrels. In short, with T1, we could have one large sphere do the work of 25 small ones. What could this mean in actual savings? Weight of shell material, 66% less. Shell surface area, 66% less. Cost of shell material, 14% less. Weight of manholes, fixtures, and so forth, 96% less. Weight of structural supports, 38% less. Concrete for foundation, 14% less. Lineal feet of weld seam, 70% less. Ground area covered, 84% less. And we've said nothing about reduced shipping costs, labor costs, and maintenance costs. There is no exact way to measure these items. But it's obvious that when T1 is utilized to its fullest potential, the possible economies are tremendous, and far from being purely hypothetical, it has proved itself in hundreds of applications in the field. The more far-sighted builders and designers were the first to benefit from this new advance in steels, but T1 has now reached such widespread use that even the most conservative recognize it as a versatile and lusty young giant, which can open the door to new products, improved performance, substantial economies, and give us a new freedom from the confines of conventional steel. For T1 is more than just another steel. It is a new concept in steel, a new engineering material.